The next type of graph we want to look at are exponential functions. Remember, functions, meaning it's going to pass the vertical line test, and as we're going to see, these will. Now, to be exponential, we're going to say f of x, remember being a function. An example we're going to look at is 2 to the power of x. Exponential functions are when our exponent are our variable. Now, we talked about how to use a table to graph, and we're going to use a table to graph for this one just to see exactly what's going on. We talked about earlier the best number is 0, 1, and 2. I will go to 3 this time just to see what's going on. But we talked about how -1, -2 are better, and we're even going to go with -3 this time just to get a firm grasp of what's going on. Now, when we start with our positive numbers, 2 to the power of 3, as bad as we want to say 6, remember that means 2 times 2 is 4 times 2 is 8, which remember means ordered pair, 3, 8. So when we look at a graph here, we go over 3 units, we go up 8 units. Now, when we plug in that 2 squared, that's going to be our 4. Remember, ordered pair, 2, 4. Well, 2, 4. When we plug in the ordered pair 1, 2 to the first power, anything to the first is itself, meaning ordered pair 1, 2. Now, just to look at this side of the graph right now, think about what's going to happen. As we put in 4, it's going to double again, 16. As we put in 5, it's going to double again, 32. As we put in 10, 2 to the 10th power is 1,028. Not only are we off the graph, we're probably even outside of the room right now. This graph gets so steep, so quick, it's difficult to even picture the full magnitude of how this graph even looks. And that's a term, if you ever heard grow exponentially, that's what's happening. This right side is growing so quickly that it's almost difficult to even graph. Well, where it gets more interesting, 2 to the 0 power. Remember, as badly as we want to say 0 or 2, anything to the 0 power, 1. Ordered pair 0, 1. And in fact, all of the base exponential functions are always going to have that ordered pair 0, 1, because that's following right in line with that properties of exponents. Anything to the 0 power, 3 to the x, 4 to the x, 5 to the x, 20 to the x. If I had those all to the 0 power, 2 to the 0 is 1, 3 to the 0 is 1, 8 to the 0 is 1. Anything that I would have as a base, the 0 power will always be 1. That's where we're going to start most of our graphs. But here's where it gets even more interesting. 2 to the -1 power. Remember, as badly as you want to say -2, negative exponents mean reciprocals. 1 over 2 to the positive 1. 2 to the positive 1 is 1. This means -1, 1/2. Meaning left 1, and it's only even up half a unit. It's not even up a full box. Well, look at when we have 2 to the -2. Once again, a reciprocal. 1 over 2 to the positive 2. Well, 2 squared is 4, meaning ordered pair -2, 1/4, which means left 2. Up a fourth is barely even off the line. In fact, trying to draw it, it's smaller than the tip of the pin. When we talk about the 2 -3, that's going to be 1 over 2 to the 3rd power, which again we want to say, but you'll notice that it's mirroring, right? The 2, the 4, the 8. That's again just because it's just a reciprocal of that number. 1/8 is what 2 to the 3rd power is going to be. That means go left 3. That up an 8 is hard to even draw at this point, but it's going to keep getting worse. And what's going to happen is you'll have 1/8, 1/16, 1 over 32, 1 over 64, 1 over 128. What's going to happen is this keeps getting closer to and closer to and closer to and closer to. It's never going to touch and it's never going to cross. And that's an interesting concept, because to think that it's getting smaller and smaller and smaller, but it's never going to touch it and it's never going to cross it, is a weird concept. It's almost like the fact that what's called Archimedes' razor, when you have half an inch and you cut it in half, right? You got a hair, cut it in half, cut it in half, cut it in half, cut it in half. You'll always still have a hair, and maybe you'll have to zoom in and you'll still be able to cut it in half, cut it in half. Maybe you'll have to zoom in again, cut it in half, cut it. Eventually you'll have something that it's hard to even see, but maybe you'll even put it under a microscope. Zoom in again. You can always keep cutting things in half, cutting things in half. That's what's happening here. Remember what it means to actually touch. To touch the axis means I would need a 0. When I keep taking reciprocals, the only way to get a 0 is to have a 0 in the numerator. 0 in the numerator is never going to happen because when I take the reciprocal of a negative number, even 2 to the negative 100, the negative 100 is just going to be 2 to the positive 100 in the denominator. It's still going to be that 1 in the numerator every time. I'm never going to be able to touch the axis. And even more, it's never going to be negative. That's why it's never in that lower quadrant, because the only way that it's going to cross down is if one of those numbers ends up being negative. But since we're only taking the reciprocal, nothing's ever going to be negative. It's just going to keep getting closer to and closer to. This is what's called, in math, an asymptote. Now let's look at how to sketch some of these graphs. We won't ever want to do the table. We're just going to want to follow the same mold for the graphs of exponential functions.